Hello, everybody. This is a lecture on group actions and Burnside's lemma. And this is going to be the final topic for the course. I was hoping to do a little bit more, but circumstances being as they are. Okay, so here's the definitions. Let G be a group and X a set. So X is neither a group or a ring or anything special. It's just a set of elements. G is a group and X is a set, although it can be any set. We say that G acts on X. Acts on X. When? For every G and H in G and element little x in big X, this right here, that means the action of G, it's not G times X. So Gx is read as the action of G on X. Abstractly, that's what it's read as. Right? Or you can say like G of X, or something like that. It's not group multiplication, although it can be. It's the action of G on X. And you'll see examples of what I mean in a moment. Okay, so the action of G on X is, again, an X. So the elements of the group are permuting the elements of X. Well, not permuting, but they're moving around the elements of X. Okay? The action of the identity on X is just X, so the identity element's fixing everything. And the action of H on the element resulting from the action of G on X is the same as the action of element HG on X. Okay? Example. So the basic example is, I mean, we've seen group actions already. It's really a generalization of what symmetric groups do. Let G be a subgroup of the symmetric group on n symbols. Then G acts on the set 1 to n by defining the action of pi on I is just pi of I. The action of pi on I is just pi of I. Okay, so that's the group, and that's a set. And again, the set is nothing special. It's just a set of elements, 1 to n. No addition, multiplication, subtraction, anything like that. And the action is that pi takes I to pi of I. Okay. Now, when you give X some geometric structure, things become more interesting. And this is the main type of example I'd like to go over. All right. Let X be the set of these vertex-labeled squares. So how did I get these vertex labels? I took the square and just named the vertices A, B, C, D, and then I applied all of the dihedral symmetries to it. Rotating this 90 degrees gives me that. Rotating 180 gives me this. Rotating 270 gives me that. Reflecting around horizontal line gives me this. Reflecting around a vertical line gives me that. Reflecting around the horizontal line gives me that guy. Reflecting along this diagonal gives me that. And reflecting on this diagonal gives me that. Okay, so now it doesn't have to be that. I could just label all of the do all possible labelings of the square with elements A, B, C, D. Okay, but I'm just taking these. Now let G be the dihedral group of order A, the symmetries of the square, which is as a subgroup of S4. So I want to look at the dihedral group of order A as the group generated by rotation 1, 2, 3, 4 and reflection 1, 3. Now, what do I mean between A, B, C, D and 1, 2, 3, 4? So I don't want to get like these labels, A, B, C, D. So A, B, C, and D are in different spots, right? A is here, B is here, C is here, D is here. But now A is there, B, C, D, and so on and so forth. So in a square, put symbols 1, 2, 3, and 4 here, always in this position. 1, 2, 3, 4, always in that position. And define an action of G on this ABCD square by labeling the corners of each square and then moving the square by the elements of G and then erasing the labels 1, 2, 3, 4. Right? So if I took this guy here, the action of 1, 2, 3, 4 on this square, which was in X. So that's 1, 2, 3, 4. So this takes the vertex at position 1, puts it at position 2. The vertex at position 2 puts it at position 3. Vertex at 3 puts it at 4. And the vertex at 4 puts it at 1. Or vertex 2 puts it at 3. The vertex 3 puts it at 4. And 4 puts it at 1. So now 1 goes to 2. 2 goes to 3. 3 goes to 4. 4 goes to 1. And then, this BADC goes to CBAD. And then just erase those guys. So add the labels 1, 2, 3, 4, permute the labels according to the dihedral symmetry, and then erase them again. So I don't want to get the corner labels and the 1, 2, 3, 4 labels mixed up, and that's why I'm being careful like this. Or another example, the action of 1 goes to 2 and 3 goes to 4 on this guy here. Well, this is position 1, that goes to position 2. All right, so swap positions 1 and 2. So the B and the A get swapped, and swap positions 3 and 4, so the C and the D get swapped. So that's reflection around that horizontal or vertical line. Okay, what else can I do? Rather than labeling the corners of the square, one could label the edges of the square instead. Okay, one doesn't have to label the corners. One could label the edges. Okay. Now, let the dihedral group, okay, and I'm going to use for the edges 5, 6, 7, and 8 rather than 1, 2, 3, and 4. Okay, so this is edge 5, 6, 7, and 8. So now the permutation, 5 goes to 6, goes to 7, goes to 8, goes back to 5, takes the square and rotates it 90 degrees in the clockwise direction. Okay? So 5, 6, 7, 8 takes this square to that square. Rotation 180, 5, 7 to 6, 8 takes this to that. Right? So PQRS here, rotate 180, and you're at the bottom, PQRS. Rotate 370, PQRS, it's rotating backwards 90 degrees. Notice there's a little bit of a difference here. Okay, this square right here, I obtained from this square here by doing a reflection around the horizontal or the vertical line. So when I rotate around that, reflect around that vertical line, P and R stay the same, although they got flipped, although it doesn't matter according to the labels. P and R stay the same, they get fixed, and then Q and S got exchanged. So the permutation is this. Right? This is 5, 6, 7, and 8, so 6 goes to 8. Notice that that's a little bit different than what happens with the vertex labels. With the edge labels, reflection around this horizontal line is 2 cycles. Switch these 2 vertices, that's a 2 cycle, and then transpose these 2 vertices, that's a 2 cycle. Here I got 2 fixed points, 2 fixed labels, and then 2 swapped labels. So it's just 6 goes to 8. Right? So the same geometry gave us a different type of permutation. Reflection around the horizontal line gives me this, where 8 and 6 are fixed and 5 and 7 are swapped. And then reflection around that line, P and S get swapped, R and Q got swapped, so it's 2 cycles. Whereas for the vertices, these 2 are fixed, and then it's 1 2 cycle. And then reflection around here accomplishes this, and that corresponds to that permutation. All right. So let D8 be equal to this, where 5, 6, 7, and 8 have this meaning, like before. And then that's an action of G, which is the dihedral group order 8, on this set X of labeled squares. Okay. So you could label vertices, you could label edges. Oh yeah, define the action of G on X as before. Okay. So we labeled vertices, we labeled edges, right? Squares with vertex labels, squares with edge labels. What about both? What if we did both? So this is example 3, this is example 4. So in example 4, we will label the vertices as well. Rotate 90 and you get this, A, B, C, D. Rotate 180 and you get this, A, B, C, D. Rotate 270, you get that. Now flip around the vertical line, right? P and R stay the same, and then A and B get swapped, and D and C get swapped. Reflect along the horizontal, D and A get swapped, and C and B get swapped. Around here, well, A and C stays the same, and then D and B get swapped. And then the other, so A and C get swapped, B, D. All right, so X is the set of squares with edges starting with this label, edges and vertices labeled, and then applying dihedral symmetries to that to get all these other labelings, the 8 total labelings here. All right, now let G equal D8, but this time as a subgroup of S8 based on the labeled square So the vertices we're going to have labeled 1, 2, 3, 4. Edges labeled P or 5, 6, 7, 8. So G is equal to, okay, well, you have the identity. And now rotation of 90 degrees. 1 goes to 2, goes to 3, goes to 4. 5 goes to 6, goes to 7, goes to 8. Rotation 180. 1 goes to 3, 2 goes to 4. 5 goes to 7, 6 goes to 8. Rotation 270, 4, 3, 2, 1, 8, 7, 6, 5. Reflection on the vertical. So reflection on the vertical line. 1 goes to 2, 3 goes to 4 for the corners. But then S goes to Q, or Q goes to S. And then P and R stay the same, or 5 goes to 7. Along the horizontal, the reflection. 1 goes to 4, 2 goes to 3, and edges 5 goes to 8, or 5 goes to 7. This one was, these two, 6 goes to 8, sorry. That was for that guy. Yeah, so 6 goes to 8, 5, 6, 7, 8. So this one, which was reflection along the horizontal, 5 goes to 7. And then there's this reflection, right? B goes to D, A and C are fixed. And then 5 goes to 8, 6 goes to 7. And then that reflection, 2 and 4 are fixed, 1 and 3 got, 2 and 4 got switched, 1 and 3 got swapped, 2 and 4 are fixed, 1 and 3 got swapped, and then for edges, 5 and 6 replaced with 7 and 8. So that is, and now define the action of G on X as before. All right, so I can talk about the dihedral groups as actions on vertices of the square, or the regular n-gon, actions on edges of the regular n-gon, or both at the same time. And you'll see a nice application of this in just a little while here. Okay, so that was example 4. Example 5. So I'm not going to go over these in any detail, but in example 5, one moment. In example 5, a group G acts on X on itself in various ways. For X equal to G, or X equal to a collection of subsets or subgroups of G, or X equal to the set of cosets of some subgroup. So there's various different kinds of actions of a group on itself. And then these actions form the basis for the proofs of Cauchy's theorem. And Sylow's theorems. But we won't talk about these here. I want to go over the combinatorial applications of this stuff, just to make a little bridge between this course and the combinatorics and graph theory course. We actually did one of these actions of a group G on itself when we did the proof of Cauchy's theorem. So G acted on itself by conjugation, right? So the action of G in G on H in X, which was equal to G, was G, H, G inverse. And we used that to help prove Cauchy's theorem. And we had this thing called the class equation within there, right? Because this is called the conjugation, and you had conjugacy classes, and you had this class equation. So this is all kind of a generalization of those ideas. Oops, I messed up something. No, we're okay. Okay. So, but I don't want to go over those. I just want to go over these geometric things. Okay. All right. So the various examples of group actions. Now, definition. Given a group G acting on a set X, for little x in the set X, define what's called the orbit of X to be equal to the set of all Gx such that G is in G. So it's all the elements of the set that X goes to. So X, it goes and visits a whole group of different elements in X, and you call that the orbit. So it's kind of a nice name. So the orbit of X. All right. Some facts. One, X itself is an element of orbit. X. Two, either for all X and Y, either orbit X equals orbit Y, or orbit X intersection orbit Y is empty set. All right, so what do 1 and 2 say? So 1 and 2, they say 3 is that the orbits of the action of G on X partitions X into disjoint subsets. So that's just a combination of 1 and 2. Every element in X is in some orbit, and then any two orbits are either the same or completely disjoint. Okay. Proof. 1, well, the action of the identity on X is X. So that's it. 3 follows from 1 and 2. So we just need to prove number 2. Okay, so let's take X and Y. Such that orbit X intersection orbit Y is not empty. I mean, if it was empty, we'd be done. Okay, say that Z is an element of orbit X intersection orbit Y. Okay, since thus there is G in G and G and H in G, such that the action of G on X goes to Z, and the action of H on Y goes to Z as well. Right? Therefore, Gx is Hy, so H inverse Gx equals H inverse Y. Right, but then you can regroup things, right? So this becomes H inverse G X equals H inverse H Y, and so that's the identity. And then the action of 1 on Y is just to leave it alone. Therefore, Y is in the orbit of X. Now, for any other z in orbit y, there is g and h and g. Maybe we should say a and b this time. Such that ax is y and by is z. Right? Z is in orbit y, and y is in orbit x. So some group element, the action on x goes to y, and some group element, for some group element, the action on y goes to z. So now, z is equal to b times y is equal to b times ax is equal to bax. Thus, z is in orbit x, because the action of BA on x goes to z. So, orbit y is a subset of orbit x. Similar reasoning shows orbit x a subgroup of, or subset of orbit y. Okay. So that's that. So the orbits, they partition the set X on which G is acting. All right. One moment. I'll be right back. Okay, we're back. All right. So, definition. Given G acting on X and little x in X, let the stabilizer of X be equal to the set of all Gx, or the set of all G in G, such that Gx is equal to X. So that's called the stabilizer of the element X. And this is a subset of, well, it's going to be a subgroup. It's a subgroup of G, different than the orbit. Right? The orbit, the orbit of X, it's the set of all Gx, such that G is in G. These are in X. This is a subset of X. So I could add that in there. That's a subset of X. The orbit of X. The stabilizer of X. It's all the group elements whose action on X leaves X alone. Stabilizes X. All right, and then the proposition is that stabilizer X is a subgroup of G. Proof. Exercise. Okay, it's just proving something's a subgroup. It's no big deal. All right, so that's a subgroup of G. But then the big result here is the following theorem. So this is called the orbit stabilizer theorem. The orbit stabilizer theorem. And it says the following. If G acts on X, and both are finite, this all goes out the window if they're not finite, and both are finite, then for every little x in the set x, the size of the orbit of x times the size of the stabilizer of x is equal to the order of g. Okay? Orbit stabilizer theorem. Okay? The size of the orbit of x times the size of the stabilizer is the order of g. Very nice result. Proof. Since the stabilizer of x is a subgroup of g, right? We are trying, well, so we need to show that that orbit x is equal to the order of g over the order of the stabilizer of x. That is, show that orbit x is the index of the subgroup stabilizer x in G. All right, so the size of the orbit is actually the index of the stabilizer, is what that is saying. Okay. All right. So why is that the case? Well, first of all, no, this is the proof. Is the index of the subgroup of G, that is, stabilizer, orbit X is the number of cosets. We'll do left cosets. Just cosets, doesn't matter, left or right. Cosets of stabilizer X in G. Right? So somehow the elements of the orbit must represent the elements of the orbit must somehow represent the cosets of the stabilizer. Okay? All right. So suppose that let G and H be in G. Now, the coset G stabilizer X is equal to the coset H stabilizer X if and only if H inverse G is an element, right, of stabilizer X. Right? If and only if H inverse G, the action of H inverse G on X is X. If and only if the action of G on X is equal to the action of H on X. Okay, so two cosets are the same. Two cosets of the stabilizer are the same when the action of G on X is the same as the action of H on X. Now, write orbit X. So what is the orbit of X? It's everything that X goes to under the action of G. So it's the action of the identity on X, and then the action of G1 on X, and the action of G2 on X, Gm on X. Maybe I'll just put a G1 here. G1 up. No, just a 1. Right. Write the set orbit of X like this, where Gix is not equal to Gjx for I not equal to j, right? The orbit of x is the set of all things in x that you can get to by the action. So there's this element y. There's some element, there's x itself, right? The action of the identity. And there's some element that takes you to this element y over here. Then there's some element that takes you to this element z over here. Say it's g1 here, say it's g2 here, so on and so forth, where gix is not equal to gjx for I not equal to j. Right? But that means that the cosets are different. Right? This gx is equal to hx if and only if the coset g stabilizer is the same as the coset h stabilizer. Right? Thus, gi stabilizer x is not equal to gj stabilizer x for I not equal to j. Therefore, the cosets of stabilizer x are in one-to-one correspondence with the elements of orbit x. So orbit x as required, basically. So orbit x is equal to the number of cosets, which is that. Okay, as required. Okay. Orbit stabilizer theorem. Very nice. So when I started graduate school, this was like one of the first topics that really sort of caught my attention, and I really liked, and it got me going in the direction of working in combinatorics. I like group theory a lot, but then I more so wanted to do combinatorics after seeing this and its various applications, in particular the ones that apply to combinatorics. So that's the orbit stabilizer theorem. Okay. All right. Now the big theorem here in this section is the following, and this is Burnside's lemma. And I don't know, it's usually called Burnside's lemma. Sometimes it's called other things. But it's a theorem actually due to Frobenius. By Frobenius in 1887. So most of the mathematics that you learn as an undergraduate, was developed, like 300 years ago or more. And it takes a little while to get up to the 20th century. So we're almost here, 1887. So as far as mathematics goes, this is actually like relatively new compared to like calculus and differential equations and stuff that you learn as an undergraduate. Anyway, Burnside's lemma. Say that, we needed one definition before we do Burnside's lemma. One definition. So similar to the idea of the stabilizer is this thing called the fixer. So say group G acts on X for X in X, define for G in G, define the fix of G, the fixed set of G. It's the set of all X in X such that Gx equals X. All right, and this is a subset of X. So the the fixed set, the fixed points. And so G acts on X, and then for a group G, for group element G, the fixed points of G, it's the set of all X and X, such that the action of G on X is X. So similar to the idea of the stabilizer. The stabilizer, right, is the stabilizer of X. It's the set of all group elements G, such that G fixes X. Right. So here X is fixed, and we're looking for the elements of G that satisfy this property. Here, the group element is fixed, and we're looking for all these things in the set X, which G fixes. So that's a subset of X. Okay, and then Burnside's lemma. Say that G acts on X, and both are finite. The number of orbits, not the size of the orbits, the number of orbits. The number of orbits of the action is 1 over the order of G, the sum over all elements G in the group, fix G. Okay. So that's Burnside's lemma. Actually, first proven by Frobenius. Okay. Maybe I should make a part 2. Yes, I will. Okay.